input that we get. So if you don't have any writing utensils or you didn't collect a feedback form, we'll have them available at the front. And sort of the nice, good, warm feeling you get from doing something good is an incentive. We also have cookies. So if you hand in the forms, you get a cookie. In addition to the talk that we have tonight, we also have Planetarium shows afterwards. I think I might still have a few tickets, which you can ask about after the talk. If you collected the Planetarium tickets on your way in, just make sure you show up at the meetup place by the time it's on there. I'll do another reminder at the end of the talk. We also have refreshments and some demos. Normally we do observing, but I believe it's going to be rainy and cloudy all night. But normally we get to look through our telescopes. So for tonight's talk, we have Dr. Tova Yost-Ho. She's a postdoctoral fellow here at the Canadian Institute for Theoretical Astrophysics, or CETA. She did her undergraduate degree at Kenyon College in Ohio and her graduate degree at the University of Wisconsin-Madison. In her free time, in addition to being a spectacular expert on cosmic rays, which she's going to tell you all about tonight, she also plays the trombone and the tuba, and she also enjoys quilting in her spare time. So let's all give Dr. Yost-Ho a warm welcome. Thank you.
Okay, great. It's fantastic to be here tonight. Thank you for coming. So I'm going to talk to you tonight about the world of cosmic rays and what they're all about, how we detect them. Talk into the microphone. Yep, okay. Nope. How is this? Okay, there we go. That sounds better. Yes. All right, so I'm going to tell you all about cosmic rays, what they are, how we detect them, how we look at them, how we, where they come from, how we make them in the first place, and why they're important. So I'm going to start with some background material so that we can understand what cosmic rays actually are. So hopefully I'm starting on familiar ground with the periodic table. So if you had a high school chemistry course or a college chemistry course, hopefully you've seen this. If not, then I question what your chemistry teacher was doing. So start off with, we have in the top left-hand corner is hydrogen. Hydrogen is the most abundant element in the universe. About 74% of the elements, matter in the universe is made up of hydrogen. So in the periodic table, right, we have the element name at the bottom, so that tells you what it is, and it tells you how many protons are in the atom, and we'll get to what a proton is in a minute. Abbreviated symbol, which is normally what you would expect based on the name, but occasionally it's not, right, because iron is right here, it's abbreviated as Fe, and you've got gold, which is Au. So occasionally you have strange Latin names for things that have different abbreviations. In the center at the top is the atomic weight. The atomic weight of hydrogen is the weight of just more than one proton. It's 1.008, I think, yeah. And then the atomic number is the corner top right. Right, so we have all of these wonderful elements that make up the universe. Let's see, 23 to 25% of the universe is helium, and then everything else, that few percent, is everything from lithium all the way up to elements that we can only make in a laboratory. And the majority of these elements are made in stellar nurseries, in the aftermath of a stellar explosion. So some basic definitions, right? So when we're talking about elements, we're talking about atoms. So an atom is pretty much the smallest unit of an element, right? So it's got a central nucleus, very dense. It's made up of at least one proton, and if you're not a hydrogen atom, then at least one neutron. And it's surrounded by shells of one or more electrons, right? So proton, that's the positively charged particle in the center of the nucleus. Neutrons have the same mass as a proton, but have no charge. They're neutral particles, right? So, and then finally, the electron is orbiting around, and it's got a charge the opposite of the proton. So we call that -1. And this may be a familiar picture, right? So you've got the protons, the not nucleons, the neutrons in the center, and then electrons around the outer part. And so the masses, sorry, the charge of the electron and the proton are the same. The mass of the proton and the neutron are the same, but an electron is almost 2,000 times smaller in mass than a proton, which is why you often see them depicted as smaller physically. Okay, so moving on from just electrons and protons, we have groups of smallest particles, smallest elements that exist, right? So you have the smallest, so the atom can be broken down into multiple parts, right? You've got the proton, you've got the neutron, you've got the electron. Well, the electron itself doesn't break down any further, right? So we call that an elementary particle. Any particle that doesn't break down into something else is an elementary particle. And an electron is actually part of a big family, right? So we have this particle, it's got the same charge, but it's got a lot more mass. So the muon weighs about 200 times more than the electron. And then we have this particle called tau, and a tau is 2 million times more massive than the electron, right? And this will be a trend. We'll put up more particles as we go along here, and as you go to the right, particles get more massive. So we have these, and they all have a charge of -1. And then we have neutral particles that are in the same lepton family, and these are called neutrinos. So for each electron, muon, and tau, we have an associated neutrino, and neutrinos are very tiny particles, right? So they weigh 4 millionths of the mass of an electron, right? So they're super small. And they have no charge, right? So they're totally neutral, which means they're really, really hard to detect. In fact, they had to build a detector at the South Pole that was a cubic kilometer to detect them from things other than the sun. So that's one family. And then we have this other family. It turns out protons and neutrons actually break down into smaller parts called quarks. And so we have some very interesting names. We have the up quark, we have the charm quark, and we have the top. Let's see. In relation to the electron again, right? The up quark is about 4 times more massive, right? So there's not a huge difference in terms of weight there. But as you get to the quarks all the way at the right-hand side, the top quark is 3.5 million times the mass of the electron, right? So it's more like the tau here in terms of weight, not in terms of its properties. And so these are the positively charged quarks. They have a charge of +2/3 in comparison to the charge of the electron. And then we have the negatively charged ones. We have a down, and we have strange, and we have bottom. And sometimes, depending on what you're reading, you might see top and bottom also be referred to as truth and beauty. Yeah. And so they have a charge of -1/3. And so usually we see them sort of, oftentimes you'll see them sort of in pairs when we talk about them. The most massive ones we'll talk about together, and we'll talk about the least massive ones together. Let's see. Okay, so we've talked about leptons, we've talked about quarks. Now, from quarks, I said that that's what a proton or a neutron breaks down into. Well, it turns out there are whole families of particles that you can build out of these quarks. And so a hadron is just a particle that's made up of 2 or more quarks. And so we can split them into 2 classes, 2 big classes. There's baryons and there's mesons. Baryons have 3 quarks or 3 antiquarks. I'll talk about what antiparticles are in a minute. And there are mesons, which have 1 quark and 1 antiquark together. And it really doesn't matter what these terms are, but in large part, but we're going to see particles that are baryons, and we're going to see particles that are mesons throughout this talk. And so cosmic rays can be any of these. An antiparticle is a particle that, say you've got a proton. Well, there's an opposite particle called an antiproton. It's got the same mass, it's got the same composition, same everything, but it's got an opposite electric charge. So this will come up later. The most antiparticles are just called anti, and then whatever the name of the original particle is. But the electron we call the antiparticle positron, because it's positively charged, right? So it's got the mass of an electron, but it's got the charge of a proton. Okay, right. So protons you can make from 2 up quarks and 1 down quark, and neutrons 1 up quark and 2 down quarks. And we're going to talk about pions later on, and they fall into this category of mesons, and usually it's 1 up and 1 anti-down, or variations on that theme there. And then we also have this particle called a kaon sometimes, and that's distinguished from the pion because it has a strange quark of some kind in the mix. And there is a property that I really don't know anything about called strangeness, so there is a reason why they called it strange. It's because it's got really odd things that happen when you have those types of quarks. Okay, so back to something a little more familiar. And then I promise we're going to get to what the heck a cosmic ray is. So we're also going to talk a little bit about radiation in this talk, right? Most of the stuff that we see in astronomy is light of some kind, and this is the electromagnetic spectrum. You may also hear me later on talk about photons. Photons are just light. They're special little bundles that run around and do super interesting things, but it's not any different than radiation of some wavelength, right? So you've got familiar types of radiation. There's radio, there's the stuff we can actually see, that's called the visible light, that's this little bit in here. We've got infrared waves, there's ultraviolet waves, and at the high energy end, there are X-rays and there are gamma rays. So at the extreme ends, you've got the radio, and that's everything below a certain wavelength or at a low enough energy. And then at the high end, anything above a certain energy, and we're not really sure what the defining energy is, because the division between X-rays and gamma rays is a little bit nebulous. But above a certain point, you fall in the category of gamma ray, right? And so the wavelengths of these particles, so the measurement of this wave packet from the top of one to the top of the next wave gets tiny at the upper end and really big at the low end. So some radio waves have a wavelength, length of a soccer field. And gamma rays, it might be smaller than the size of an atom, right? So we're talking about big changes in energy and big changes in size when we go from one end to the other. Okay, so what the heck is a cosmic ray? So let's start back with the helium atom. So again, you've got the proton and the neutrons in the center, which is the nucleus. And in the case of the helium atom, you have 2 of each. And you've got electrons, 2 electrons that orbit around. And if you throw energy at it, if you throw enough energy at it, what happens is you can separate the nucleus from the electrons. So the electrons detach and go flying out in space and do their own thing, and the nucleus goes in a different direction and does other stuff. So if you take that nucleus or you take those 3 electrons and you add lots more energy, you get a cosmic ray. So basically a cosmic ray is just a nucleus, a proton or a free electron moving at very, very high speeds. And I will talk about how high speeds in just a minute. But first, a little bit of history. So cosmic rays were originally discovered in 1912 by Victor Hess. So what he was doing was he was going up into the atmosphere in this balloon and he was measuring what he thought was radiation. And he noticed that as you go up in the atmosphere, you get more and more radiation. You detect more and more of it. And so one of the ways they were detecting these particles was with the cloud chamber, which had been invented the previous year. And I'll talk about how we do that later on. But basically, in the GIF here, you're seeing radon gas injected into the chamber, and the subsequent interactions of the particle and the decays is all the different streams and things like that going on, right? So the term cosmic ray was officially coined in 1928 by Robert Millikan. And then in 1932, the positron was discovered. Before that, we didn't really know about antiparticles. And remember, positron is the antiparticle of an electron. So Victor Hess and Carl Anderson won the Nobel Prize for the discovery of cosmic rays and the discovery of positron in 1936. And then Anderson went on to discover muon with Niedermeyer in 1937. So the 20s and 30s were a really busy time for cosmic rays. And so we've talked about what a cosmic ray is. Let's briefly go over what a cosmic ray isn't, right? So this term was coined in the late 20s. And originally they thought cosmic rays were a form of radiation, right? So turns out they're not. They're not gamma rays, they're not X-rays, they're not anything you're going to see on the electromagnetic spectrum. They're not radiation or light, which are the same thing, right? Cosmic rays are particles and only particles, and they're charged particles mostly. So they're super energetic, and how energetic, you may ask? This is the next slide. So first we're going to talk about what they are. So we talked about how they're protons, we talked about how they might be nuclei, and they might be electrons. Well, 86% of them are protons. 11% are helium nuclei. About 1% are the nucleus of other atoms, say oxygen or carbon or silicon or iron or magnesium. 2% are electrons, and less than 1% are positrons, anti-electrons, or antiprotons. And so we can measure the flux, we can detect these particles at Earth, and we can turn that into a graph of how many we're detecting versus what energy the particle has. And so at the low energy end, you're detecting about 1 particle per square meter per second. Shooting lots of cosmic rays all the time. But if you're at the very high energy end, you're detecting 1 particle per square kilometer per century. Yeah. So if you have a detector that's only a square kilometer, you're going to have to wait 100 years to see more than 1 particle, which means instead of waiting 100 years, we build really big detectors, right? And so basically what this is showing is that, you know, as you go up in energy, there are fewer and fewer of these particles. And here is a plot with some actual data, right? So here is, these are mostly protons up here, and then you've got all these different experiments that have been detecting cosmic rays, and you can see the breakdown of electrons, positrons, antiprotons. And we'll talk about galactic versus extragalactic later on, and one of the more important things here is right here, this is the energy of the LHC. So the energy that the LHC, which is at CERN, which is in Geneva, so it's the Large Hadron Collider, we talked about what hadrons are, right, is accelerating particles, and that is the maximum energy that they can accelerate to, right? And so we detect particles that have even more energy than that by at least a factor of 100. So the universe can make really energetic particles. We're not quite there yet. Okay. So we talked about how you can get cosmic rays that are various kinds of nuclei, and how protons or hydrogen is the most abundant, right? And it's the most abundant by far. This is way less than 1, and this is way bigger than 1. And so it's the same periodic table before. If it's in gray, it's not a cosmic ray that we've ever detected, but everything else we've detected in cosmic rays. And so you can see it goes all the way up past iron, which is right here, and goes all the way up to, I believe that's zirconium, but I wouldn't swear to it. And the most abundant ones, right, are hydrogen, helium, and things like carbon and oxygen. Carbon and oxygen would be because you make those kinds of elements in stars, right? So you're going to have a lot of those in comparison to all these other elements. Okay, so we have talked about what cosmic rays are, and we talked a little bit about energy. So when astrophysicists talk about cosmic rays, they like to talk about them in terms of their energy, in terms of electron volts. Now, what the heck is that? So kilowatt hour might be something you're familiar with if you have an electric bill. And so it's way smaller than that, right? but let's put this in terms of things that, you might actually encounter in your daily life that are not ridiculously small. So a volt is the amount of energy you gain by moving, oh, no, this is the definition of a joule. I'm sorry. So something like a kilowatt hour is related to how much energy you gain by moving an electron across a potential difference of 1 volt. That's what an electron volt is, right? Volts. So a battery, AA battery, is 1.5 volts. Your plug for any kind of appliance you have plugs into the wall in US and Canada is about 120 volts. In Europe, it's 230. Power lines are hundreds of kilovolts, and lightning is a megavolt, mega meaning a million, right? So 1 electron volt is a very, very small cosmic ray, very, very slow moving cosmic ray. It's not even a cosmic ray. So plot on the previous page went from 10 to the 9 electron volts all the way up to 10 to the 20, right? So we're talking a lot more than 10 to the 6, which would be a million. So 10 to the 9 is a billion electron volts. And so we tend to talk about particle masses in terms of electron volts. That's because mass is basically energy, right? You've probably seen the phrase E equals mc squared somewhere, right? Einstein, it's a big deal. But basically all it means is mass is energy, right? If you can convert it into something else, it would have a lot of energy. So proton has a mass that is equivalent to a billion electron volts. And an electron has a mass that's equivalent to 500,000 electron volts, right? So it's a lot more energetic than things we're talking about over here, and it's a single particle, right? When we're talking about your plugs or lightning or power lines or any of that stuff, we're talking about lots of electrons moving through power lines. Here we're talking about a single particle, and that's the amount of energy that we're imparting. And so if we want to talk about this in terms of speeds, right? A particle that has 10 million electron volts is moving at 20% of the speed of light. The speed of light is 300,000 kilometers per second, right? It's really fast. And it's the speed at which light moves in a vacuum. And nothing else can move as fast as that or faster than that. If you have a billion electron volts, then you're moving at almost 80% of the speed of light. And so as we go up in energy, we get really, really close to the speed of light. Close enough that I don't really know how many 9s there are right there. So, and that's for a single particle, remember? And so the largest cosmic ray we've ever detected had an energy of 3 times 10 to the 20 electron volts. And that's equivalent to about 1.3 kilowatt hours, right? And that's a single particle. Lots of energy, it's moving very fast. So that's what cosmic rays are, right? So it's not just about a particle that's moving quickly, it's about a particle that is essentially moving at the speed of light, or as close to it as you can get. So how do we detect these particles? Okay, so I talked about cloud chambers a few slides back. So a cloud chamber, it's a sealed box, and inside the box you've got air or gas that is supersaturated with water vapor. So what that means, supersaturated, say you have a glass of water and you have some sugar and you put some in and it dissolves all the way. And so you put more and more sugar in until no more will dissolve, right? And so that's called saturated. But if you heat it up, you can add more sugar, right? So then that's saturated. But then once you cool that off, usually you get rock candy, and that's called supersaturation, right? So that's how that works. So you've heated it up, you've added enough of a dissolvable that is completely dissolved, and then you've cooled it back down, so it's oversaturated, supersaturated. So we use this to detect charged particles. And a schematic looks something like this. There's water vapor or alcohol vapor, and it cools, and the particles move through here, and as they're moving through, they ionize particles around them, the cosmic rays do, and then those ions, water vapor condenses on them, and so you can see a little trail of ions where the cosmic ray was. And so here is video of a cloud chamber. And so the really straight ones are nuclei, or they're protons, or they're muons. And the ones that get curly and spirally are electrons or positrons. And depending on which way it curls, that'll tell you whether it's an electron or whether it's a positron. I don't remember which way is which. And you'll see some of them. There's one over here that's been sort of forking, right? And that's a particle that's decaying into other particles. Okay. So, sort of talked around it a little bit, but what happens when a cosmic ray interacts with things? So when a cosmic ray comes into our atmosphere, which it does frequently, it'll hit a nucleus of some kind, oxygen, nitrogen, something, and it creates a shower of particles and a shower of radiation. And so we no longer use just cloud chambers, we use all this radiation that I'm going to talk about to detect them, to detect the original cosmic ray. So it produces pions and kaons. Remember we talked about that when we talked about mesons. So they have one quark and one antiquark, and they don't live very long. They decay super quickly into muons. Those were the heavy electrons, right? And positively charged muons are the antiparticle, right? Because regular muons are negatively charged, like an electron. And when a pion decays, you also get neutrinos. And so this is the muonic component, because at the end, you've got lots of muons and some neutrinos. And then the main cosmic ray keeps going down, knocks into things, and creates a hadronic cascade, which just means the proton's doing lots of stuff. And at the end, you've got protons, you've got neutrons, you might have some more kaons, you might have some pions. And so, right, so we made pions and kaons, and those are positively and negatively charged. We also make neutral particles. So there are neutral pions and neutral kaons, and those are even more unstable than the charged ones. They decay much quicker. And so the charged ones make more muons, and those muons, sometimes they live and they interact, and sometimes they decay really quickly, which I guess I left for a minute. The neutrally charged things, right, decay into gamma rays. So a neutral pion makes two gamma rays to conserve momentum, right? So it's moving in this direction, so then the gamma rays go off like that. And gamma rays sometimes decide they don't want to be a gamma ray anymore, and they make a pair of a positron and an electron. So you get one of those together. Sometimes it just happens. And sometimes the muon decides not to live very long and decays into an electron or a positron and more neutrinos. And sometimes that positron decides that it's going to annihilate itself with an electron and make more gamma rays. So you get a whole electromagnetic cascade, so it keeps bouncing back and forth between positrons and gamma rays and electrons, all kinds of good stuff. In addition to this whole mess of particles that you get, right, and it's a really big shower, you also get some ultraviolet radiation, you get Cherenkov radiation, which I'll talk about in a minute, and you get more, you get the gamma rays that we talked about, right? So you get lots of different particles, and you get lots of different types of radiation. And so it's mainly the footprint of these electrons and positrons, this Cherenkov radiation, and the gamma rays, and actually the fluorescence that we use to identify cosmic rays when they come in and hit the atmosphere. And then we can use that, the shower is very collimated, right? That means just it's not really big and wide, it's very narrow. And so we can use that to trace it back in the direction that it came from, which turns out to not be very helpful. I'll get to that in a minute. Okay, so Cherenkov radiation. Okay, speed of light we normally talk about is about 300,000 kilometers per second. That's in a vacuum. So it turns out when you're light and you're moving in something other than a vacuum, it slows down. So the speed of light decreases when you're in anything other than a vacuum. So speed of light in air is almost the speed of light in a vacuum, but it's a little bit less. And as you get into denser and denser objects, denser and denser media, the speed of light slows down even further, right? So C is what it is in a vacuum, and then, so in water, you're moving at about 75% of that speed. In a diamond, it's like 40%. And that's mostly just for interest, not for useful properties of anything. Remember back to the cosmic rays, we talked about velocities. They were way bigger than this, right? So that means if you have a cosmic ray and it's moving through the Earth's atmosphere and it's created this shower of particles, some of those particles are actually moving faster than the speed of light in air. And that means that they create this special kind of radiation called Cherenkov radiation. So that's just a particle's moving faster than the speed of light in that medium. And it's got this nice blue color that's a signature of that. And so we build detectors to detect this light specifically. And that tells us how fast the particle was moving and where the particle was coming from. And so we can do this with cosmic rays, we can do this with gamma rays, and we can do this with neutrinos. Okay, so different types of detectors. We still use balloons. They're still actually pretty useful. So we put all kinds of detectors and stuff on them, and we go down to Antarctica, and we launch them into the air, and they hang out in the atmosphere for a while, circling, and collect all kinds of great data. And so CREAM here stands for Cosmic Ray Energetics and Mass. We're great with the acronyms. There's PAMELA, which is in space. It's a satellite orbiting the Earth, and it stands for Payload for Antimatter Exploration and Light Nuclei, Astrophysics. It's a great name, yeah. Voyager, right? Launched in the 70s, I think, yeah. And it went to the outer solar system and saw Jupiter and Saturn and all kinds of cool things. And it recently exited the solar system, and it's still sending back data about cosmic rays all these years later. So it's actually very cool. There is the High Altitude Water Cherenkov Observatory in Mexico. So it's filled with a lot of water tanks, and water tanks are there so that when those that electromagnetic cascade hits the water tanks, then they create Cherenkov radiation inside the water tanks, and then we use special kinds of camera-like things to detect that light. They're actually not cameras, they're called photomultiplier tubes, but that's not really important. So we do that in Mexico, we do that in the South Pole. So on top of the Ice Cube Observatory, they have this thing called IceTop. Mostly it's used to detect cosmic rays and to detect gamma rays so that we know that when things happen in the main detector underneath the ice, that it's not a neutrino. And then there's Telescope Array, which is in Utah. And these are some of the detectors. So some of them look super cool, and some of them just look like a bench. Anyway, so if you really want to build a great cosmic ray detector, build a neutrino detector, because they can detect everything. And there's a lot of other detectors that are both on the ground, that are in space. So we've got balloons as well. We have great names: CREAM, Tiger, Tracer, PAMELA, AMS, Gamma, High-Res, all kinds of very creative acronyms. Okay, so where are these things coming from? So I'm going to talk about three main sources of cosmic rays. The sun. Turns out they actually come from very nearby. Supernova remnants. So this is what happens when a massive star explodes. Supernova remnant gets left behind. And active galactic nuclei. Basically, the centers of some galaxies are sucking energy into the center of them and ejecting stuff in jets. We'll talk more about that in a minute. So low energy cosmic rays come from the sun, right? And so you can sort of see these. So it's a big ball of plasma, right? Plasma is the fourth state of matter. So we've got solids, which the particles in the solids are moving kind of slow. And then you have liquids, they're moving faster. Air, they're moving, really fast. I guess it's not just air, it's gases, right? And then plasma, you've reached a level beyond that. So super fast moving particles, although not like cosmic rays, not that fast. And you can sort of see some of the magnetic field lines here, the little loops and stuff. So there's gas moving along those lines. And solar flares make cosmic rays. So sometimes the sun burps a little and ejects some gas and some cosmic rays along with them. And sometimes there are coronal mass ejections, so it blows out a whole lot more stuff right there. And so what's happening here is called magnetic reconnection. So sometimes the gas is moving up to the surface and it's bending the magnetic field lines. And when it bends the magnetic field lines, they snap apart and reconnect to the other parts down below. And it's this reconnection that gives off a bunch of energy and accelerates particles. And so I say low energy, that means 10 to the 7 to 10 to the 10 electron volts. So speeds of about 20% to 99% of the speed of light, right? So these are the low energy things. So you might think that in times of more solar activity, we'd see more cosmic rays. The opposite is actually true. So this line here is tracing the number of sunspots from the sun, and the blue line, which is the opposite of the green line, is tracing the number of cosmic rays we measure at Earth. So what's happening is when the sun is not doing very much, the magnetic field it's emitting is not very strong. And so cosmic rays can cross that and move down into the Earth, into the atmosphere, and then interact with all kinds of things. But when the sun is doing a lot of things, it's got a lot of sunspots, it's, ejecting lots of mass from it in coronal mass ejections, etc. It's got a really strong field, and that field deflects the cosmic rays. Remember, these are charged particles, so a magnetic field is going to either forward them in or repel them out, depending on the orientation. And so we don't detect a lot of cosmic rays, but we have basically you get aurora, right? You see a lot of activity with the northern lights, and that's because what happens is this plasma goes around the Earth's magnetic field. It causes part of the Earth's magnetic field to reconnect, and then that jumpstarts particles at high energies that get funneled down into the Earth's north and south poles, because that's where the magnetic poles are, right? And so that's where the magnetic field is basically vertical up and down, so they get funneled right down and they create an aurora. So you're not detecting lots of cosmic rays, but you are seeing super cool things north and south pole. So these are lower energy cosmic rays. These are things that are nearby. Moving a little further away, when a massive star explodes as a supernova, it leaves behind a remnant, and you get lots of pretty pictures. So this is a supernova remnant in the Large Magellanic Cloud, which is, or maybe the Small Magellanic Cloud, I get those two mixed up, but it's basically a little tiny galaxy that orbits our galaxy. And based on the size and the shape of this thing, we estimate that it the massive star that created this remnant exploded about 5,000 years ago. There are things that we have actually recorded in our history books, right? Tycho was a supernova that exploded in the 1570s, so they studied that a lot in Europe. I'm sure other places as well, but it's named for Tycho Brahe. There is Cassiopeia A, which was, they think it went off in the 1600s. They definitely, they're not really sure when, because they noticed it at the end of the 1600s, but they think it went off in like the 1650s or 60s. There's the Crab Nebula, which there's actually records of this in Chinese historical records and Japanese records. I think there are even drawings of it in Native American caves and things like that. First Nations up here. So there are records of that from all kinds of different places. These things would have been really bright in the sky, right? There is this one, which looks kind of cool, which went off about 1,000 years ago. And this one is from, I think it's from the SMC, the Small Magellanic Cloud, and it went off, about 4,500 years ago. There we go. So you've got all different ages and all different kinds of things. The last one that we saw that happened in the Milky Way happened in the 1600s, not this one specifically, but we haven't had one since then. We're overdue. we're supposed to get about 1 a century. And so this is what happens. It explodes, and it ejects gas, and it creates a shock wave. And as that shock wave expands and moves through the galaxy, it sweeps up gas, and it accelerates particles. So that's the explosion. And you can still see these remnants expanding, I think, maybe. Yeah, it's not moving very much, but no, it's not moving at all. Okay. Anyway, you can see them expanding. So you can like look at them over time, and you can see it's not moving a whole lot, but it's moving a little bit. And okay. Nope. Okay, I think I broke it. Yeah, it totally froze. Okay. So, no, it's not the projector, it's the...
Your computer?
Yeah.
I'll just restart it and improvise.
Okay, let's see if... Sorry for the technical difficulty. It didn't like that video.
Shame.
Ah.
Just restart your computer.
Yeah. Oh, no? Okay.
Let's do it silent.
Morse quit. Okay, there we go. There it is. Sure.
We're good, thanks.
No, it just froze, that's all. All right. Give me 1 second. No, shit. Not again. Okay. I'm gonna skip the slide. So,
Do you have a way to start it from the next slide?
yeah, it was supposed to, and I forgot to do the right thing. So, okay. How do I do this?
Just start it from that slide. Let's start it from that one.
Alright, what if I do that and that? Okay. Alright, apologies. Video was too much for it. So, shockwave is expanding through a small part of the galaxy, and it's sweeping up lots of matter, and this matter gets accelerated by the shock front. So it bounces back and forth and gains energy each time, and eventually it gains enough energy that it can escape the shock wave from the supernova remnant, and it's a cosmic ray. Yay. And you can see evidence of the shockwave from supernovae over time. This is from a supernova remnant that went off in the late 80s, and we're still seeing evidence of the shockwave into the 2000s. So we talked a little bit about particle interactions. What else can cosmic rays do? So sometimes a cosmic ray proton or nuclei is moving through the galaxy, and it runs into some gas, and it creates a new particle called a pion. And we talked about how these pions decay. They make muons and neutrinos and gamma rays. The electron, sometimes if it's a cosmic ray, it'll get pulled in by a nucleus and pulled around it, and that accelerates it. This is because of the charge difference, right? This is a helium nucleus. It's got +2, and this is just -1. So that difference in electromagnetic charge pulls it around the nucleus, and so it's accelerating, so it gives off some radiation, gives off a gamma ray. And sometimes electrons bump into photons, so they bump into just light radiation hanging around in the galaxy, and they transfer some of their energy to that radiation and make it into a gamma ray. And I think there was a slide before this one that I skipped. So basically, what happens, or maybe it's after this one. Nope, I skipped it. So what happens is galaxies have magnetic fields in them, right? And cosmic rays, as we said, are charged particles. And so charged particles will follow magnetic field lines, and they get scattered, right? So they bounce around, and so by the time they get to Earth, they're coming in a direction that is totally different from where they were starting from, which means we can't use cosmic rays to trace them back to the source they're coming from, right? So if we have a cosmic ray coming in from this direction, it's probably not coming from the supernova remnant that ejected it. It's coming from somewhere else. So that's why the previous slide was important, right? We have to use these other particles or radiation to study the cosmic rays sometimes. So in this case, we're using gamma rays to do studying. This is a neutron star. It's a pulsar, which is a rapidly spinning neutron star that emits pulses of radiation. So massive star collapses and explodes as a supernova, and sometimes that stuff in the middle turns into a black hole. Sometimes it turns into a neutron star, which is just a star made of neutrons. And so as it spins, it's got this magnetic field, and so it's emitting radiation out the poles, right? Because those are where the magnetic field lines are vertical, so that's where things can escape. And as it spins, these poles or jets are either facing towards us or facing away from us. And so when they're facing towards us, we see a lot more things happening, right? We see a lot more radiation. So we get pulses. And so the background here is just the regular visible light and maybe some infrared emission that you would see in the galaxy. And then the pulses of pulse radiation there is the gamma rays that we're detecting. And so we can see these things with all kinds of different wavelengths. So we've got radio emission, and so radio emission is caused by cosmic rays sometimes. Gamma rays are always caused by cosmic rays. And then you have all this other stuff, right? So you've got the visible part of the remnant, and then in the gamma rays you get the pulsar, and you get some of the pulsar and some other stuff with the X-rays. Basically the electromagnetic spectrum tells us about the light and the gas, but it also tells us about the cosmic rays, which is pretty cool. So this is a really recent map of the Milky Way in visible light. And so you can see the disk, right? And you can see the center of the galaxy here. And this is what it looks like in gamma rays. You can still see that disk, right? You can kind of see there's a little more something happening maybe in the center. You see a couple of bright spots here. So these bright spots are, you're actually looking straight down one of the spiral arms. So that's why there's a little bit more of a buildup there. And some of these things up here are actually external galaxies. And one of the interesting things we can see in gamma rays are called gamma ray bursts. So sometimes when the star collapses and turns into a supernova remnant, it emits a burst of gamma rays. And so we pick them up and they look a little bit like this. So at least we think that's probably the main source of gamma ray bursts. There are some other sources of gamma ray bursts that we're not really sure what they are. They may be active galaxies, which I'll talk about in a minute. but basically it's a short burst of gamma rays, very intense, and we can see it usually in other wavelengths, but gamma rays where they were first detected. Okay, so those are sometimes coming from our galaxy, those are sometimes coming from other galaxies. So how do we tell the difference between cosmic rays or associated radiation that's made in our galaxy and cosmic rays that are coming from other galaxies? So, as I said, cosmic rays are charged particles, and they stream along the magnetic field line. So they spiral around this magnetic field line as they're moving, and the radius of that spiral, how big or how small that circle is called the gyro radius. So it's just how big this circle is, right? And if you're not very much energy, you're going to be really, really close to that magnetic field line. If you've got a lot of energy, you're going to have a huge gyro radius. So how do we tell whether or not cosmic rays are galactic or extragalactic? Mostly, if the particle has enough energy, the gyro radius is bigger than the galaxy, so therefore it is definitely coming from somewhere else, we think. And so these cosmic rays are called ultra-high energy cosmic rays, which is actually the next slide, and we think they're probably coming from active galaxies. So this is a nearby galaxy. This is M81. And in the center, it's got a supermassive black hole. Most spiral galaxies have a supermassive black hole in the center. We have a supermassive black hole. And for some galaxies like ours, it's just sitting there, right? Just kind of hanging out. But in some galaxies that we call active galaxies, it is pulling in lots and lots of matter, and it's transforming that matter into energy. So about 40% of the energy that's coming in is transformed and released. And it's released in these jets, and in the jets, they create shocks, and the shocks accelerate cosmic rays, and then the cosmic rays come and hang out with us. And these are sometimes called radio galaxies. M81 is not a radio galaxy, so these are galaxies that are really far away. And what's happening here is, you see the little bright spot in the center? That's the galaxy. That's the whole galaxy right there. That's not just the center part, that's the whole thing. So it's ejecting gas, it's ejecting radiation, it's ejecting all kinds of stuff along these jets, and these jets are really big, right? So they're several times the size of the galaxy. We've got all kinds of different detections of these things. And so those ultra-high energy cosmic rays are detected by us at Earth. And so we talked about how cosmic rays sort of bend around and, maybe don't come straight at us. For the really high energy ones, it doesn't matter what the size of that magnetic field is, doesn't matter how strong it is, they're coming straight to us. They're not getting deflected, they're not getting scattered. We can trace them right back to where they were. But there's a lot of different things in the sky to see, right? So blue contours are just the part of the sky that this specific telescope can look at. And the red points are active galaxies. And the black circles are detections of ultra-high energy cosmic rays. And so some of these line up kind of nicely with some of these active galaxies, and some of them, it's just kind of an empty hole there. So we're not 100%, not even going to use percentages, we're not super sure what all of these ultra-high energy cosmic rays are coming from, but it's likely that a large fraction of them are coming from these active galaxies getting accelerated in jets. And we are at the end. So cosmic rays are super interesting, right? They are the fastest particles in the universe. They come from near, they come from far. They create particle showers in our atmosphere, which we can detect with Cherenkov detectors and other kinds of detectors here at the South Pole, in space, with balloons. Right, here's a cascade. They can tell us about supernova explosions. They can tell us about active galaxies and the associated jets, because it turns out jets are kind of hard to study and we don't know a lot about them, so we can use all the information we can get. And they're the main particle that's going to make gamma rays, right? So anything you see in the gamma ray section of the electromagnetic spectrum, there was a cosmic ray. going to leave that here. Any questions?
So maybe just for the audience in terms of time, we'll take 3 questions. But Dr. Yostal will be here for a few minutes after that while we're still collecting forms and moving on to the next portion of our evening. We will try and get those 3 questions spread throughout the room. And just remember to repeat the question.
Yes. Okay.
So you can choose.
Oh, he had his hand up first, so.
On the last slide for this, you had the list of something, like you said not the one after that. The list, the one that shows the list. You're saying that the cosmic rays, they disperse in the atmosphere.
Uh-huh.
But I thought, don't they get deflected by our magnetic field?
Yes, they do, right? So that's one of the things that's keeping them out a little bit, and the atmosphere helps them from getting all the way inside, but they've got a lot of energy, so sometimes that magnetic field isn't enough to keep them out. And depending on your latitude, you're going to see more or less of them. I think it's latitude. Whichever the vertical one is. If you're closer to the North Pole or you're closer to the South Pole, there are going to be a lot more cosmic rays because the magnetic fields are vertical, and so they won't be keeping them out. But if you're at the equator, you're going to see less cosmic rays making it through that magnetic field because the lines are perpendicular, so they're going to bounce off, basically. Yes. You?
In one of the slides, you mentioned that it gets through our atmosphere when it is cold and cloudy.
Yeah, so they were trying to associate, the question here was that one of the slides talked about cosmic rays coming in when it's cool and cloudy. That wasn't the best diagram. Basically, they were trying to associate times of more solar activity with more clouds, I think, if I got it right, and less solar activity with fewer clouds. I don't know that there's really much evidence for that connection. I don't know how much evidence there is for that connection between solar activity and weather, and I don't know that there's a whole lot of connection between cosmic ray activity and weather. Although it is definitely something that they talked about and theorized about in the 1920s. There's a newspaper clip somewhere with Millikan theorizing that they can predict the weather with cosmic rays. I don't know that they actually can. I don't think they can.
Don't think it interacted with the activity in our atmosphere, like the thunder and.
So I don't know that they're really interacting with like thunder and lightning, but lightning gives off gamma rays. And we can see that with the Fermi Gamma Ray Space Telescope, detects gamma rays from all over the place, and it detects cosmic rays too. And it can detect lightning flashes on Earth, which is super interesting. You, over there. So I think the question is what direction, or do they go in all directions, right? Oh, okay, when is it a supernova explosion spherical versus non-spherical? So we're not really sure how often it's super circular versus totally asymmetrical. When it is circular like that, cosmic rays radiate in all directions, right? And if it's not quite symmetric, spherical like that, the regions where the remnant is more intense, they're going to radiate more from there and less from the sides, but they're still going to radiate in all directions. No. They would, okay, radiation radiates in all directions, sorry, but they're charged, so they're going to follow the magnetic field lines. I take it back. So whatever that magnetic field is doing out of the star or in the galaxy, the cosmic rays are probably going to head in that direction of the field. But they're going to be produced all over the place.
Okay, so I'll just ask for a few more minutes of your patience. Would you mind switching to the other slides we have?
Oh, yes.
Okay. So a couple of things. So one for the Planetarium shows. So we have the meet place is by the elevators. So make sure you're by the meet place by the time that's on your ticket. If you didn't get a chance to grab a ticket, there's a possibility that there will be some drop-in spaces. So just ask our Planetarium ambassadors about that. And if I could get the Planetarium ambassadors to wave. So if you have your show right away, Martine here will be leading your group over. If you have a 9:30 show, Victor will be leading your group over, and then again for the 9:50 show, it is Martine again. And then we have, in addition to the Planetarium shows, we've got refreshments upstairs and a few demos as well. If you get a chance to fill in the feedback form, we have some, we'll have some spares and also some pencils to do that. And let's thank Dr. Yost Hall one more time.